Hi, welcome to this lecture. This time we're gonna tackle where or the applications of the integral. Oops. This is applications. Okay. So for this specific lecture, we're gonna first tackle the application of integration in finding areas. Area. Okay. As you can see, plane areas with regular shapes like square, rectangle, the triangle, the circle can be found using our known formulas in using precalculus. Precalculus formulas. Okay. However, there are certain figures or areas that are not regular in shape. Especially those areas that is bounded by curves. Let's say we have this and we have the curve. This curve represents by some function, and say we need to find the area bounded by this curve, and this is not regular shape unlike these examples here. So we need the another technique aside from precalculus for us to compute the area bounded by this curve. Okay. Therefore, we will gonna use the integration to solve this kind of problem in knowing the area of this figure. Actually, the problem in finding areas like this, the area bounded by some curve, led to the formulation of the concept of the definite integral. So the definite integral is based from this concept. So let me draw another illustration. See, we have x and y axis here, and there is a continuous and a negative function defined by y is equal to, say, some function of x, and need to determine the area bounded by this curve from only point A to point B. So we need okay, and let's represent this whole area here as our R. Okay, the R is the area bounded by the curve. Y is equal to fx from point A and B, from point A to B. Okay, so how can we know this area? Let me redraw it again. Some function of y is equal to fx from a to b. Okay. So using our precalculus, we know how can we um, find the area of basic shapes, right? Like this square, and for this instance, let's try this rectangle here. Okay, so we can approximate the area um, of this region bounded by the curve by using our basic shapes. Say area of this region can be approximated using the basic shapes. And we know that the formula for this is the length times width, or the side 1 multiplied by side 2 of this particular shape, right? So we can get this area here, and that is approximately the area of this entire um, entire region bounded by the curve. But we have some extra region here, right? But for approximation, we can say that this AR here, or the area bounded by this shape here, can be somewhat approximated. Okay, so how can we determine this points or this lengths? So this length here can be uh, assumed with height equal to the f of x, right? At this point of the curve, the f of x is this length or the height, and then the approximated uh, point from A to B is that since this is from x-axis, so we have, say this is our x, and this point here is our x of n plus 1, right? Or you can say that this length is equal to delta x. Okay, so this point minus x is delta x. Okay, and by getting this approximated area, we have the height times this length is f of x times the b minus a, or the delta x, right? Okay, but as you can see here, we can have a better approximation if we will use a smaller strips of rectangle x then y. Sorry, say they are equal. Say they are same curve from A to B. Sorry for my drawing. We can have a better approximation of this area by getting a smaller strips of rectangle. Say we have this rectangle here, and rectangle here, plus some rectangle here, also rectangle here, right? So by getting a smaller and smaller strips of this rectangle can give us a better approximation of the entire region that we want to approximate with, right? So say this is from point A to point B, we have some from x sub 1, we have x sub 2, x sub 3, x sub 4, up to x sub n plus x sub n plus 1, right? So at the same time, we have to determine the height f of x1, this one, f of x2, f of x3, up to the f of xn, n number. Okay. And then, in order for us to sum the areas by this small strip of triangles, so we need to sum to get the total area by these smaller strips of rectangle. So we need a f of x1 multiplied by the delta x1, so we have x sub 2 minus x sub 1, then plus f of x2 multiplied by delta x sub 2, so we have to this f of x multiplied by the other delta of x, and so on and so forth until we've complete all of these rectangles, right? And all you need to remember is to we can approximate this area by assuming each element, this height is equal to f of x times this width equal to delta of x, and then we'll get the summation from I to n. Okay, as the n is the number of rectangular strips, and the closer the the I mean the rectangular strips, as these rectangular strips approaches to infinity meaning it gets smaller and smaller and smaller strips, then it can be now equal to the area of the region R, right? So we can write this as the area is the limit as n approaches infinity. So we have the summation of from I is equal to 1 to n, the formula for our area. Okay, as the limit of n approaches to infinity, right? And by a fundamental theorem of calculus, we can now use the integral with summation of this n from point 1 to point 2. So we need to sum those areas from point 1 up to this point. So we need to sum all of these small strips from point 1 up to point 2. From point 1 to point 2. And we can rewrite this using our integral sign. Definite integral from a to b, need to define the f of x multiplied by our delta x. Okay, as this delta x approaches to 0. Okay, so that is the finding of areas bounded by curve using our definite integral. So So on the next video, we will gonna use this formula in order for us to solve a an area bounded by a curve from point A to point B. So see you on our next video.